Okay, so I would like to pass it off to our speaker for today. We have Clement Fung, who is currently a postdoctoral research associate in S3D, and who's also affiliated with SciLab, the Security and Privacy Institute on campus. He'll be presenting on his recent work in industrial control system security. So I will let you take it from here.
Sure, thank you. There we go. Get all this to work.
Yeah. Hopefully it'll be painless.
Awesome. Okay, yeah, good afternoon, everyone. Welcome to the new semester. I'm very happy to have you all attend and to learn about my work. Today I'm going to cover kind of really my whole PhD thesis. So I also did my PhD here at CMU in S3D about improving the effectiveness of machine learning for industrial control systems security. Even though this is the privacy seminar, this talk is going to focus quite a bit on security. I'll have some privacy-related takeaways at the end, but I still think it'll be very interesting for a general audience. So here in the United States, I would say that there's a critical need for us to approve recording. Okay. There's a critical need for us to secure our critical infrastructure. You may know of some high-profile cases of attacks on systems that provide critical functions such as electricity, oil and gas, or water treatment. For example, in 2021, the Colonial Pipeline was compromised, which shut down oil production in part of the US for several days. Even more locally, here in western Pennsylvania, in Aliquippa, a water treatment plant was compromised by a foreign adversary and disrupting water production. In fact, these attacks are both wide scale and very common. So in a recent study by the US government, in a 6-month period from 2023 to 2024, there were dozens of attacks on critical infrastructure. And like many problems kind of in the world today, I think a common thought is that we could use technologies like machine learning to help secure critical infrastructure systems. So, looking at a very broad view, if you have a system of critical infrastructure, such as an oil and gas plant, a water treatment system, or the electric power grid, and you're to collect data from this system and feed it to some machine learning model, when these attacks actually occur in your system, you could use this machine learning model potentially to predict some useful predictive insights for security. So, is an attack actually occurring? What part of the system is vulnerable right now? Are we about to experience a catastrophic failure? And what should we do about it? Various researchers have proposed studies kind of to address these different types of tasks. But in practice today, I would argue that machine learning really isn't useful yet in practice. So, just getting a broad sense of practitioners' perspectives of machine learning, you might hear things like that machine learning make too many false alarms to be used in these systems. It's opaque, untrustworthy, we don't know why it's making certain predictions. It's too expensive when it comes to data, or it's just too hard to integrate with these existing legacy systems. So right now, I think we're taking these data sets from critical infrastructure, making this big leap of faith, and hoping that machine learning can kind of learn all this complexity and nuance when we're training these models. Instead of kind of just hoping that data properly represents these types of operations, my research focuses on actually bridging this gap more closely. So bridging the gap between approaches proposed in machine learning research and actually the task of securing our critical infrastructure. And I would argue that the best way to actually bridge this gap is not to kind of invent, the stronger, better machine learning models. I would argue that we actually already have machine learning models that can perform well for these types of tasks. Instead, the problem is that we're not really applying them well today in practice. So my research focuses really on two major topics when it comes to bridging these areas. First, focusing on investigating what happens currently in practice to help inform and design new machine learning-based approaches. And secondly, when these new approaches are developed, to ensure that they're actually evaluated in settings that properly match what happens in practice. So in my PhD thesis, I had 4 major works, and really towards these two goals, I'm going to talk about different various parts of these And what my PhD thesis really focused on, more specifically within critical infrastructure, is industrial control systems. And so I'll provide a quick overview of what that looks like and an overview kind of the different parts of my thesis. So an industrial control system, right here is shown on the right, and interfaces with a physical process like an oil and gas system, water treatment, etc. These systems read sensor information from these physical processes. So, the pressure of a pipe, the level of a tank, and run computation to send commands back to these physical processes, such as turning on a valve, closing a pump, increasing the flow rate, etc. If you were to take these sensors and command values and send that all as process information to a machine learning model for anomaly detection, as suggested before, you could use these models for security relevant tasks to detect anomalies in this process data. And when something looks wrong or off in this process information, and I'll go into more detail later about what that could mean, you send out an alarm, an alert. And right now, if you were to look or read most of the papers in this space, the story kind of just ends here. You have alerts that just get sent out into the void, and sure, maybe they're very accurate. There's a very high accuracy. You're able to detect many events. But that's just kind of where the story ends, if you were to read many papers in this space. In my work, I take a broader view and actually look across this full operational workflow. And I'll talk about 3 major projects that do so. First, I look at actually what happens after these alerts are sent out from the operator's perspective. So, there's a human actually involved in this whole loop, and they have to actually look at these alerts, interpret what's going on, and respond accordingly. So the first part of this talk, or the first piece of work that I'm going to focus on, is a study where we actually interviewed various operators in this space and investigated what their needs are for managing their alerts. One thing we found was that operators need a little help with managing their alerts. And because of this, we proposed the use of explanation methods or explainable AI or attribution methods as explanations to help operators with diagnosing alerts. So in the second part of this talk, I'll cover another work where we focus on explaining ICS anomalies with machine learning methods. And then finally, after finding that these models and explanation methods kind of were just being applied off the shelf today, we found that there was an opportunity to actually improve them with domain-specific knowledge. So actual ICS relevant knowledge, both from the physical process and the control system itself. And the third part of my talk, I'll talk about an in-progress work, or actually in-submission work, about designing ICS-specific ICS models and techniques. So I'll just pause quickly if there's any questions about the scope here before I start diving into these various parts. Yes?
So can you briefly comment on the frequency at which people are likely to see these alerts? I assume that there are also false positives, which is probably why you want to have explanations.
Yep.
And I was wondering, what would be a typical, level of number of alerts per day
Yeah.
you might have to process?
Yeah, getting a little ahead of the stuff in part one,
sorry.
but we did interview various operators and ask them these types of things, and it really varies, I think. So it kind of depends on, let's say, how big of a system they have, the populations they're serving. But this could be as infrequent as 1 or 2 a day, up to, let's say, hundreds an hour, right? We really talked to participants that had that diversity of experience.
Potentially another question, you might answer it too later, so feel free to say.
Oh, sure, yeah.
So you've mentioned explanations, which makes a lot of sense.
Yeah.
I was wondering if these explanations also consider the risks. That means this is the reason why, I'm flagging an alert, and by the way, these are the potential things that could be going on, and these are the potential consequences. Is that something that you've explored also? Or?
Yeah, so the way that we're actually applying these is actually to help guide operators to diagnose the sources of anomalies. Consequences is a little less part of this project. I'll kind of talk at the end about different challenges for why. But yeah, thanks for the questions. Okay, surveying the room. Now I'm going to go into the first part of my talk where I talk about this work where we investigated operators' needs in ICS. And I guess when you're diving into this area of research, probably the first thing that you might ask, and definitely the first thing a reviewer might ask you, is whether or not machine learning is actually used in practice today, right? So we're proposing these machine learning methods. Are they actually used, right? In that blue box, in practice today, is there a machine learning model actually raising alerts to operators? And in a recent industry survey, so in 2024, there was an institute that surveyed various ICS operators in this space, and they found that generally the adoption of machine learning for this task was relatively low. So only 10% of respondents said that they were using machine learning in any way to help with securing their ICS networks. And then another 19% said that they were experimenting with it, which was, without much more detail than that, let's say. So I'd say today the adoption is much lower than what these research papers might be suggesting. And in fact, what's done instead of training these machine learning models is that operators will manually write different rules for detecting anomalous behavior based on the same process information that's being collected. So for example, you might write that if the tank level is above 5, raise an alert to an operator. Like that's in practice what actually happens today. And kind of naturally, there are some disadvantages of this type of approach, right? You can only detect behaviors that are explicitly defined. So someone actually has to know that the tank level being above 5 is the problem and write that into their detection set. And secondly, it's also very labor intensive to write, not only write, but to also manage. So if you were to suddenly buy a bigger tank, you have to update all the rules for that tank. And we found that both of these are actually issues that operators found in practice, getting a little ahead of myself. So given these disadvantages, this work really wanted to focus on investigating why machine learning isn't being adopted today in practice. And to do this, we actually directly interviewed practitioners who work in this space. So to do this, we recruited from a variety of channels, including social media and sending emails to mailing lists related to ICS security. And we were able to recruit 18 participants, 13 of whom actually worked for operations for a single ICS. So day to day, their job was to manage a water treatment system or the power grid. And then 5 additional participants who actually worked as vendors. So they worked across ICS, developing technology and actually selling them to various utility providers. And our participants spanned multiple industries, including electricity, oil and gas, manufacturing, and water treatment. Diving into this work right away, we found an immediate challenge, which is that there are very few practitioners in this space that actually knew much about machine learning. So it turns out if you actually get an interview with one of these people and ask them why they're not using machine learning, they really don't have much to say. They don't really know why or what exactly you're talking about just yet. So because of this, we took an indirect approach in our interviews, and we did this with semi-structured interviews, where we asked instead about just their day-to-day tasks, so what technology and tasks they're actually performed for alarms, how new technology just in general, not machine learning based, is adopted into their environments today, and then their general perceptions of what machine learning even is and what using it in their environments might look like. And then based on this, we did rounds of qualitative coding and analysis for themes relevant to adopting machine learning.
What sort of education do these people have?
I'm sorry, I missed the...
What sort of education do these people have?
So everyone here at least had, let's say, like specific training when it came to managing ICS and like kind of the process part of it. In terms of actual machine learning knowledge, very, very rare, I think.
Do they have college degrees, or it's more like more associate degrees?
No, I think at least, I don't know for sure, we didn't like totally record it, but my impression was that they're all at least, let's say college educated in like an engineering or style program, yeah. But it was maybe like nuclear process, like very focused on that engineering side.
Right, okay.
Okay, so after interviewing these practitioners and doing these rounds of qualitative coding, I'm going to talk about now what we actually learned from these interviews. And I'm going to group our findings into 3 major categories. First, I'll talk about the different technology and infrastructure used today, both for actually collecting and processing data from the physical process itself, and for building out systems for raising these alarms. Next, I'll also talk about the human factors of these tasks. So actually how humans are involved in the process of alarm management and collecting and responding to these alarms, and then various pain points about these tasks. And then finally, I'll comment directly about perspectives on machine learning adoption itself, both from the perspective of how vendors are currently integrated into these environments, and perspectives on how machine learning could actually help with their tasks today. In this talk, I'll give a brief overview of each of these 3 categories. There's a lot more details that I can talk about in follow-up questions, or if you're curious, you can even read this paper. So I'm happy to talk about that more, maybe offline. But first, let's dive into technology and infrastructure used in ICS for alarms. And what we found was that alarm systems used in ICS come in really many different shapes and sizes. So it's really common that these systems use rule sets, these manually written detection rules, but how they're actually used really varied. For example, participants reported using different types of logic. So whether or not a process value was too high or too low, whether it was changing too quickly, and even using combinations of these predicates. Participants also mentioned that these rules could be written in various locations. So an ICS is actually composed of many different devices and technology kind of in a geodistributed setting. So alarms could be written, or the conditions for alarms could be written directly into sensors, low-level controllers, known as PLCs, or high-level controllers, for example, SCADA. So different levels of granularity and scope. Furthermore, alarms were not always displayed where they were actually written, so they could be flagged in one device, but actually forwarded and displayed to a human in another. And then finally, the people actually responsible for writing these alarms and managing them also varied. So these could be written and managed directly by these plant owners or the people working in day-to-day operations. But we also learned of cases where these alarms would actually be forwarded to the, let's say, original vendor or manufacturer of your device, and they would be the ones responsible for actually responding to these problems. All in all, I'll summarize by saying the first takeaway here regarding technology infrastructure is that because these ICF setups vary so much, it really contradicts common assumptions of research when it comes to deploying machine learning into these settings. What I mean by that is that when papers today write about using machine learning for ICS security, it's commonly assumed that there's a centralized location where all the data and all the compute exists. And a human is looking at this one computer that just has a full view of your system. But in practice, what we learned of was a far more decentralized setting. So data, devices, and user interfaces were highly decentralized in ICS. What this means is that when you have this kind of complex interconnected systems with low-level controllers, higher-level controllers, and user interfaces spread around, and alarms possibly being raised or forwarded across various devices in this ecosystem, and different humans all interacting with this system at once, it's pretty unclear actually what the ideal location for an anomaly detection model might be. So I think there's really raised open questions about this deployment model. Next, I'll talk about human factors in managing and defending ICS today. And what we found was a set of, let's say, common human tasks that are performed in workflows when responding to an alarm. So, we set out really to ask about detection systems, how they're written, and how they're used. But we actually learned of different follow-up tasks that occur after an alarm is raised. For example, alarms are often forwarded to an operator interface, where an operator is responsible for diagnosing and determining how to properly respond to an alarm, known as alarm diagnosis, performing the correct follow-up action. And in fact, this actually was a challenge. So one participant reported that was what they considered to be their greatest challenge. For example, when training staff that's still fairly new, so newly hired into their company, figuring out what the appropriate level of response to an alarm is was actually their greatest challenge. So we found that alarm diagnosis really relied a lot on this intuition and experience. Another task that was commonly mentioned was alarm management. This is the task of taking multiple alarms raised perhaps over the last week or the last month, collecting them into a database, and then having another human look at this data to try and optimize and improve your alarm system for the future. And this again was reported as quite difficult. One participant mentioned that in their system, they looked at every single alarm that they had, challenged if you needed it, what the alarm point should be, and it actually took a year and a half of at least 10 hours a week. So that's a significant amount of labor for just managing these types of systems. So even determining what should be an alarm or how an alarm should be written turned out to be a difficult task. So our second takeaway here is that based on these challenges that participants reported, operators really want help with tasks beyond just raising new alerts into this system. Right now, a lot of research focuses on machine learning for ICS anomaly detection, detecting new anomalous behaviors and flagging new alerts. But we actually see an opportunity to use machine learning for other follow-up tasks, such as ICS alarm diagnosis or ICS alarm management. And these really are not getting much focus today in research. Yes?
So are there simulators out there where you can actually, experiment with different ways of, supporting coordination among those people, different patterns? I think I've seen simulators, but I'm not
Yeah, so I would say a full like end-to-end, including that human team element of it, going all the way down to the technical stack. I wouldn't say, at least as far as I know, isn't quite there yet. But this is like definitely an area of future work that I think needs to happen. And
So I was in Saudi Arabia, for instance, last year, and met with people from Aramco, and people who've got also in government significant budgets to manage cybersecurity. And I think that I saw some, pretty impressive setup where they're really simulating things and they've got screens for different people. And it seems like, because at the end of the day, it's a workflow issue. It's about coordinating these different people, knowing how to escalate, knowing who to show which alert to first, and allowing them to, know who to forward this to if they can't figure it out.
Yeah.
Right. It seems that there's a lot of that needed. Perhaps at some point, ML, can obviously facilitate this process.
Yeah, I think that's exactly kind of the stuff I'm suggesting. As a small side comment, I will mention that it kind of differed by industry a little bit. So you mentioned Aramco, and I would say the participants we talked to in oil and gas, I would say generally had higher budgets than, for example, your water treatment operator. And I think they're definitely in a better position to be leveraging these types of technologies. And it doesn't surprise me too much that they have kind of this high fidelity simulation, and they're kind of thinking a little ahead of it. And then finally, I'll now talk about just directly about the participants' perspectives on adopting machine learning into these systems. And jumping right to it, the takeaway here, I would say, is that practitioners are actually pretty optimistic about the potential of machine learning for ICS, but wanted to see it introduced carefully into these systems. So there was some belief that adopting machine learning was feasible for ICS, but not necessarily for detection as commonly proposed in research. Instead, practitioners preferred that machine learning be used for kind of non-critical, complex, time-intensive tasks. And they also prefer that machine learning models were used to assist and make suggestions rather than any sort of automated decisions or predictions. One participant even mentioned this, without any prompting. We have thousands of examples of the data was doing this, it led to this root cause analysis, and then it led to this action. And that's something we can begin looking at applying deep learning to because we have the necessary data to train that. So it really suggests that they're already thinking of this as a use case for machine learning. Of course, not everything was positive when talking about ML, and almost all practitioners still had at least some reservations about machine learning. For example, saying that it was overconfident, inaccurate, or just difficult to understand. And what they really wanted to see was more interactive demonstrations and model transparency in the space. So one participant mentioned that the management of their plant would not trust AI because they don't have a solid understanding of how it works. And another participant mentioned that, really towards better adoption, what they really need is to be able to get in there, do some development, make changes, and see what that really looks like in order to make them more comfortable. So summarizing the first part of my talk, we looked at operators' perspectives of adopting machine learning to protect ICS. And we identified differences between research and practice, both technical and in human factors, that today really hinder the adoption of these solutions proposed in research in practice today. We identified a common workflow around alarms, from detecting systems, diagnosing and responding to them, down to optimizing your alarm systems. And based on this, we make some recommendations. First, we recommend that researchers in machine learning for ICS really focus on these downstream tasks, such as alarm diagnosis and alarm management. Secondly, we recommend that researchers really consider the different technical and regulatory constraints as well on data collection. This will be a major barrier towards training and deploying these models in practice. And then finally, just directly from these suggestions from practitioners, to really focus on demonstrating the transparency of these models through perhaps interactive pilot projects and really involving them in this process to help build that trust. Okay, so zooming back out, I will now talk about the second part of my thesis. And yes?
You mentioned that people generally seemed optimistic about how the machine learning could be applied to ICS. You also mentioned earlier that in general there wasn't a huge amount of knowledge regarding machine learning. In order to get to the point where there was that optimism, did you have to communicate or do some level of education or provide information?
In the interviews themselves?
Yeah. And if so, what sort of things did you provide? Because I could see how that could shift the tone of their.
So we didn't design our study in the way where we kind of talked about what machine learning we were actually envisioning. We wanted to keep it kind of open and broad. I would say participants had various mental models that were all at least accurate. So some mentioned training like a decision classifier, deep learning, et cetera, based on like data that they're collecting. Some were suggesting, taking like a ChatGPT style agent that would actually help and assist. So I think they had at least a decent understanding of what was possible, let's say, with ML, and maybe needed a little more help with understanding the like deployment challenges and that type of stuff, at least from a technical perspective.
Thanks for clarifying.
Yeah, no problem. Any questions elsewhere? Okay, great. So yeah, in the second part of my talk, I'm going to talk about actually designing methods for helping explain anomalies with machine learning. Just jumping right to what I mean when I say explanations, I'm really borrowing terms from a whole other field of research, kind of called explainable AI, like broadly. And all of these, this research area is really focused on developing attribution methods. These are methods that explain what input features cause a model to produce a specific output. So in other words, when a model predicts a label, why? If you were to look at work in this space today, a lot of it focuses on the image domain. For example, if you have this image of a bird and a deep learning-based model that was trained on images of birds, it might tell you that this image is of a goldfinch. And you could use an XCI method or an attribution method to explain or answer the question, like which input pixels actually caused this prediction. And what this method would return is, let's say, a heat map of pixels. Here, white pixels or brighter pixels mean that these pixels are more significant towards this goldfinch prediction. So what we'd like to do in this project is translate or take an analogy of this use case and apply it to ICS. So if you were to have process information from an ICS and a deep learning-based model that tells you there's an anomaly somewhere in the system, we want to use explanation methods to say which sensor or actuator was actually the one being attacked or manipulated by an attacker, and to suggest areas of the ICS for further diagnosis and follow-up action. So in part two, I'll give an overview of what I'll cover. First, just because this section is a bit more technical, I'll give some background on how these machine learning methods actually work and how detection looks like today. Then I'll answer three questions. First, are machine learning models from prior work attributable? Can they be explained with off-the-shelf strategies? Secondly, how do properties of ICS actually affect the accuracy of this attribution task? And then finally, maybe a bit of a spoiler, is it possible to actually do better than what these prior strategies are actually giving you? So first, let's talk about, I'll just provide some background to help understand the rest of this part on machine learning-based ICS anomaly detection. And the threat model we're assuming is that attackers actually manipulate process values in real time to attack an ICS. So here's the same ICS from before, where it's reading sensor values from the process and sending commands to actuators in your system. And what we assume is that the attacker has some ability, whether they're compromising a controller, getting onto the network, et cetera, or even physically accessing the system, and they inject abnormal process values into this control loop. And these process values are specifically designed such that when they're read by the industrial process and they propagate throughout the control loop, this eventually causes some harmful, catastrophic failure in the system. So to defend against these attacks, many researchers have proposed using machine learning. And the way this is done is you can collect a time series history of the different sensor and actuator values during benign operation of your system, feed that and use it to train a deep learning-based model, and use this model for a forecasting task where it predicts what the next future predicted ICS value should look like. So in real time, when an attacker comes and does this abnormal value injection attack, and it's read into the data in real time, this prediction can then be compared to the next observed time step from process information. And if the prediction and the observed value differ significantly, and this is calculated through per feature mean squared error, then if the total error is too high, then we'll raise an alert. So that's kind of how these machine learning models are designed today. So next, I'll talk about what prior work is doing today when it comes to explanations and talk about how well these solutions might work. So in prior work, they take a very simple view of attributing these anomalies. So given this per feature error, mean squared error, and current input that raises an alarm, the idea is that you still have feature errors for every single feature, so you can just attribute the alarm to the feature that has the highest error. So given errors for every single input in your system, you could just say this sensor is the one with the highest reconstruction error, and that's the one responsible for the alert. What we also do in this work is we adopt XAI methods for the ICS domain. And the way that this is done is that we take these methods, for example, from the image domain, and adapt them to the ICS domain. So we take some methods that you don't need to know all the details of them, but some names of these methods include saliency maps or SM, SHAP, and Lemna. These are just methods designed kind of for other domains, not in ICS. So we did adaptation to make them work for this type of use case. And these methods all take both the time series input and the model itself as input to these attribution methods and produce a flat set of sensor and actuator attribution scores. So a score that's assigned to every single input to the model. And then in the same way that MSE can be used, we attribute the alarm to the highest attribution score in this case. When evaluating attribution, we wanted to evaluate across a diverse set of use cases. So, we evaluate attributions produced by a variety of anomaly detection models, including linear models, CNNs, convolutional neural networks, recurrent neural networks, or LSTMs. We also experimented across 3 different ICS. These include both water treatment systems, which are given as public data sets by other researchers, as well as existing simulators that we modify for evaluating this use case. And we evaluate across a variety of attacks as well. So in total, 147 attacks, both the 47 real attacks provided in these public data sets, as well as 100 newly simulated attacks from this modified simulator, which we modified and made publicly available as a part of this work. And then finally, for evaluating attribution, we proposed a new metric called average rank. And what this does is it simulates a diagnosis scenario. So given a set of sensor and actuator attribution scores, here darker squares correspond to higher values, we assume that an operator might sequentially look through these scores. So what they might do is search through these features with the highest X percentage of scores until they actually found the attacked feature. So the average rank is exactly this. It's X. It's the percentage of features that you have to search if you're using these attribution scores as guidance before you would find the attacked feature. And this also means that lower is better. So if you have a more accurate ranking based on attribution scores, operators would have to search fewer features, which ultimately means that they save time before finding the attacked feature. So that's enough talk about kind of how we did these experiments and evaluations. Let's talk about what we actually found. And jumping right to it, using the mean squared error ranking, which is what's commonly proposed in prior work, performs a lot worse than previously reported. Some prior works in this space, the way they evaluate attribution is that they just take a couple example case study attacks, and they show that the MSEs predicted by their models match the highest attacked feature. But when you're to take the same strategy and apply it to our full set of 147 attacks, you find that this would work in just fewer than 40% of cases. So in less than 40% of these cases, the highest error feature actually corresponded to the one that was manipulated by the attacker originally. In addition, operators, but using our average rank metric, operators would have to consider at least 14% of their system on average before finding the attacked feature. So, given kind of what's being shown in these example case studies, I would say the performance is actually a lot worse right now, today. So, after finding that MSE didn't exactly work the best, this prior MSE ranking, we now ask if attribution methods perform better. So we have our adapted XAI methods from other domains, and we apply them to our use case. On this bar chart, I'm just showing the average rank, where lower is better, and for 3 different models and 4 different attribution methods. And what we find actually is that attribution methods just off the shelf are consistently worse than MSE. So in each case, the orange or green bars are higher than the black bars in each group, meaning that you might as well just be using the baseline strategy based on these results. So in each case, the average rank is higher, meaning that you take more time to actually find the attacked feature. So off-the-shelf adapted attribution methods don't yet outperform baselines. So after kind of getting this initial result in this work, kind of took a step back and thought about what is it about this use case that actually makes this task so complex. In our paper, we have various findings, but in this talk, I'll just focus on one, which is actually timing. So ICS anomaly detection is a time series task, right? It happens in real time, and attacks happen over time series. And what this means, I'll illustrate this with an example attack from the SWOT data set. So this is just an attack provided in one of these public data sets. And in this attack, a single sensor value is raised to a high abnormal value from this anomaly start point and held to that high point all the way until the end of this anomaly. And this causes some harm in the system that isn't shown in this figure. But if you were to feed this input overall to a anomaly detection model, it would detect the anomaly actually fairly late. So it would take about 100 seconds before the overall error was high enough for an alarm to be raised. And given this situation and your attribution method, there are different options for actually applying this attribution method to this input in order to generate a single suggestion. And I'll talk about 3 different options here. The first option that you might consider is to apply it instantly. This is to take the very first point where an attack occurs and apply your attribution method. The problem here is that the input to this method, because it's a time series model, would actually only contain benign data. So there isn't actually any information with attacks, or very little information with attacks, that can actually be used to help explain why this anomaly is occurring. The second option you might consider is what I'll call the practical use case. So this is actually just applying attributions at the first moment that an alarm is raised. This is realistic, but let's say late, given this late detection in this example. And then finally, a third option that I'll talk about is this, what I'm calling the ideal. This is where you shift the input window to the front of the anomaly start, but still that it contains only anomalous manipulated data by the attacker. This is, I'll show it soon, but this is actually ideal for attribution, but of course it's an idealistic case. Right? In real time, you don't know when the attack starts. But nonetheless, I'd like to use it for comparison. And what we find is that the accuracy of attributions varies based on the timing strategy you're using. So here I'm comparing, again, with the same bar charts where lower is better, a lower average rank, the practical use case and its equivalent if you were to convert the same attack but explain it with the ideal timing. So that's the 50th time step because these models use 50 seconds as input. And what we see is in every single case, comparing black to black, orange to orange, green to green, the average rank lowers. So using this ideal timing outperforms its equivalent practical outcome. I'll talk about 2 additional cases when it comes to ideal and practical. First, I'll mention practical detection using late detections only. So here we take our full attack data set and we filter out cases where the attack was detected too early, kind of matching that instant case that I mentioned before. And here what we find is that by doing this, you can also improve the performance of attributions in every single case. So overall, if you're able to know and avoid these early detection cases, you actually can improve the results of your practical attribution strategies.
Can you just spend a few more seconds on explaining the performance metric that you're using?
Yes.
I assume it contains both false positives, false negatives, all these sorts of things.
Yeah, so this is kind of equivalent to looking at the CDF of your scores. So the value here, let's say it's 0.2, means that if you were to just use the ranking of all of your features based on the output of the explanation method, that you would search until you hit 20% of your overall system. So 20% of the sensors and actuators in your system until you actually got to the manipulated, the one that the attacker manipulated. And that's on average across all the attacks.
Okay.
And then finally, I'll also talk about ideal timing cases, but even cases where detection is missed. Right? So here we don't actually have an alarm, but we still know the ground truth start of the anomalies. And what we find is that the performance of attribution methods, so SM, SHAP, and lemma, is approximately the same when comparing cases where the anomaly actually is detected and cases where the anomaly is not detected. And what this suggests is that performing attribution, even in cases when an alarm isn't raised in real time, could actually be useful. This could simulate a post hoc, post-anomaly diagnosis scenario. All in all, given these results, I'll just say that attribution of ICS anomalies can improve if you decouple them from the strategy used in prior work, which is just to immediately explain when there is a detection.
But is
yes.
anomaly in this data set always bad? Or I mean, are you only taking examples that are basically true positives, or is this a mix?
Yes, so it's not in this talk, but yes, everything I'm showing here is actually a true positive for an alarm. And then there's also cases where you can use attributions to analyze false alarms. It's not in this work, but in general, that use case is a bit weaker.
You would probably want to have a mix that reflects what you have in practice, where you would have actually a mix of false positives and true positives.
Yes.
And then you would want to see how attribution works in that context.
Yes, I agree. And that's something we could definitely do more in depth in follow-up work. Okay, finally, I'll close out part 2 by just proposing a new attribution strategy that, hopefully, let's say, outperforms all these prior ones I've been mentioning. So, without any prior knowledge of what attack you're actually detecting, what attack you're actually trying to explain, and when it actually occurred, is there a best approach for attribution? And the idea here is that given that there was differences in how well different methods performed, we propose an ensemble attribution method. So what this does is it takes a weighted average of attribution scores from 3 best performing attribution methods and presents a weighted average score for every single feature. And in showing how well it works, I'm again going to show this same average rank metric, now shown over time from on average when the attack starts. And what we find is that, for example, MSC performs actually poorly at later timings. So after the attack starts, MSC performs well and becomes worse over time. In contrast, these adapted attribution methods, SM and Lemna, perform poorly at earlier timings and improve over time. And that's because of this time series history needed for attribution. And in taking the ensemble of MSC, SM, and Lemna, we can actually design an attribution method that outperforms all individual methods across this use case. And what we also find is that this doesn't rely on knowledge of the attack start. So this ensemble case actually performs the best for practical timings as well. So in summarizing part 2, we looked at attribution methods for ICS anomaly detection. We found that the performance of prior methods was worse than expected or based on what they're reporting. And this is because the task of attributing an ICS anomaly is actually quite complex. Factors like timing affect which methods will work best. But all in all, we found that an ensemble-based approach, at least for now, balances trade-offs between these methods and has this provides the best performing attributions. Okay, zooming back out, I'll now talk about a third major chapter of my thesis, where I look at ways to design ICS-specific machine learning models. And this is a work in progress. But I'll pause actually in case there's any questions about part 2. Okay. All right. So next, I'll talk about this work. The goal here was to design a machine learning model specifically for this ICS use case. And in part 3, I'm going to present a model called Cypress, which stands for cyber-physical representations with sparse structures. And I'll talk about just 2 major things. Firstly, how Cypress is actually different from these models used in prior work. And secondly, the performance of Cypress compared to these models. So first, let's give an introduction of what Cypress actually is. And first, I'm going to talk, about the design space of anomaly detection methods. This is both from talking to practitioners and kind of surveying the space of research today. Currently, what's commonly used is detection rules. As mentioned before, these are explicitly defined rules manually written by experts, which is very labor-intensive, and very precise in what is actually detected. Right now, researchers are very focused on using deep learning models for these tasks, which can detect anomalies, but in a very unstructured way, which is kind of why you need these attribution methods to help explain what they're doing. And in general, they don't require much domain expertise. If you have a data set and general knowledge of PyTorch, you can train an anomaly detection model that performs relatively well when it comes to just detecting these anomalies.
Can I ask you a question on the training data? So it sounds like you're starting with data that has been collected perhaps by that facility, or perhaps that the vendor has collected from a number of different facilities. There are clearly attacks that they've not seen yet, right? And so are you basically preparing for older attacks, and how does that prepare you for future attacks?
Yeah, so I should have mentioned this in the background part, but all these models are actually unsupervised. So they don't rely on any attack data during training. So they only are trained on benign non-attack data and are used to forecast benign operations.
Okay.
The assumption there from a machine learning theory perspective is that any significant deviation from that normal distribution of process data is enough to indicate an attack. So it can kind of detect even these unseen, unknown behaviors.
Do you want to enhance that data with simulation, or that's tricky because it assumes that you've got a model to drive the simulation? If that model is not correct,
you're hitting all my future work. But yes, yes, ideally what you want, and what I think current work doesn't do very well, is it kind of lacks this diversity even within benign operations for training.
Okay.
Yes. Okay, and then looking at this spectrum from detection rules to deep learning models, our work, Cypress, kind of falls in the middle. So what these are machine learning models with some structured constraints that kind of respect ICS behavior, but they only require a lightweight amount of domain information. So rather than requiring an expert to actually understand all the anomalous behavior that could occur, it only uses a lightweight amount of information. And the way this is done is with feature relationships and connection sets. So, these ICS govern physical processes with relationships kind of under the hood. These include both physical relationships, for example, the flow sensor of a pipe and the level sensor of the tank that it flows into, as well as logical relationships in the control logic, such as an input to a controller and then how that actually relates to the output that's fed back. But right now, prior work mostly uses deep learning for this task, which doesn't necessarily learn these types of relationships. These are just models built on dense layers where everything is interconnected, which means that any relationship can be learned between input features. And what this can lead to is what are known as spurious relationships. These are relationships that might exist in the data, but don't really make sense in reality or in practice. And we'll show later in this work that actually this can harm things like detection and attribution. So instead what we do is we design Cypress to only learn patterns from sparse structured sets of defined ICS feature relationships. And this is inspired by kind of related work in the image domain. So prior work has proposed different architectures that really have restricted image-based convolutions to really limit what input features can affect what output features. And what we'd like to do is do the same thing using graph-based convolutions for ICS process data. The way we do this is that we can represent these interfeature relationships with directed graphs kind of under the hood in this model, where nodes represent process values from sensors or actuators, and edges represent temporal relationships between these components. So internally, Cypress uses these graph adjacency with temporal relationships to represent ICS. And the way that this is done is that these models, Cypress, like other models, take this time series process input and internally learn a graph of ICS features. One way you could do this is to manually specify this graph, so define all the different nodes and edges in the graph. But kind of going back to what I just said, this is expensive and very labor intensive. So instead, for this work, what we do is we use partially specified graphs. You can have a lightweight specification of just different sets of features that might be connected or could have a relationship, and then use our training process to actually define the weights and connections between these features. And these feature sets can be based on various automated sources, such as a list of invariants, generated from an invariant mining technique, different statistical measures like covariance, or even just straight up definitions of what PLCs are in your system.
So if these models are not correct, you could completely mess up your machine learning, right?
All machine learning has the chance of being trained, I guess, incorrectly, unless you meant something more.
No, like the model of, pipe flowing into a tank. It seems intuitively to make a ton of sense.
Yes.
But then perhaps the tank has a finite capacity, and you're not representing that, and then all of a sudden machine learning will not necessarily, effectively use that structure.
Oh yeah, definitely. If you're training just generally machine learning, it's just going to have this normal distribution assumptions about all your input data, and that might involve your tank being negative suddenly, right? Even though it's kind of not seen in the training, just having that distributional assumption might lead you to that.
That's correct.
Okay, so now that I've explained what Cypress is, let's just present some quick results to show how it actually compares to prior work. And in this, I'll just present an overview of our results, many more in this paper that's in submission right now. But we're going to compare both manual versions of Cypress, so ones where me as a kind of a researcher defined a graph and used it to train Cypress, as well as an automated method that we call Cypress Gecko. This is based off of a prior invariant-based work. And we compare them to different deep learning models that I've been using in these other works, CNNs, GRUs, and LSTMs. And we're going to compare them for the tasks of anomaly detection, anomaly attribution, as presented in part 2, and new evaluations related to robustness to evasion attacks. And just giving kind of the summary of these major findings regarding anomaly detection, Cypress isn't necessarily the best model for detection, but we found that it can actually perform similarly as well as deep learning. So given our best performing versions of each of our deep learning models and the 2 Cypress variants that I just mentioned, I'll show just the point F1 and the range F1 scores. These are F1 scores that are the weighted average of precision and recall, where the point F1 is over individual sections, and range is over a time series constraint. And what we find is that Cypress is actually able to achieve not necessarily the best performance, but similar performance to these deep learning models. In addition, when considering the number of parameters that are actually used in these models, these deep learning models all use millions of parameters when you're training them, but Cypress actually only uses a couple thousand. So we're talking about 1,000x fewer parameters than deep learning models, but with similar detection performance. Moving on to attributions, I will show similar types of average rank graphs as before, where lower is better. For all the different variants of Cypress and all the variants of deep learning that we tried, and just to really summarize, on average, using Cypress consistently can provide more accurate attributions. So consistently, if you are, for example, attributing anomalies on TEP, on average, you would only look at 2.5 features before finding the attack feature, whereas there's a higher variance with deep learning. For example, the best performing model here can be up to 7.6 features for diagnosis. And considering the same thing for PLCs, Cypress would give you a consistent average of looking at less than 2 of your controllers, whereas deep learning models would be higher than that. Finally, I'll talk a little bit about robustness and evasion attacks and just kind of talk about what I mean here. So here, let's assume attackers can be a little more stealthy. So in these data sets right now, there's an assumption that the attacker compromises a single controller and manipulates a single process value, kind of as shown here. But what prior work has suggested is that there's opportunities to do what are called concealment attacks. These are attacks where you send a different set of values only to the anomaly detection model. And in this work, we additionally evaluate on the version of these where these values are optimized based off of a copy of the anomaly detection model. So this is a very strong attacker who has access to a controller and some knowledge of the anomaly detection model itself. And what we find is that by using these attack strategies, if you've done any work in adversarial machine learning, you know that these deep learning models are very brittle and very easy to fool by manipulating these features. You can achieve very high attack success rates. Whereas with Cypress, it's actually much harder to evade these models because they're so sparsely connected. So we find that deep learning models are very vulnerable to evasion, but Cypress is more robust to these same attack behaviors. Furthermore, I'll explain an even stronger version of these attacks.
You can robustify these things by randomizing them also, right? Yes,
so there are various methods kind of across the machine learning literature for making these more robust, but they're not included in this work. I'll just quickly touch on a more strong version of the attack that assumes now even that the attacker has access to your entire system. So here, let's assume that the attacker actually compromises every controller in your system and is able to send spoofed data back to your anomaly detection model. Trivially, this attack has 100% of a success rate because they could just replay training data or benign data back to the anomaly detection model. But what we'd like to know is kind of what the breaking point is for Cypress. So here I'm going to show kind of a CDF where we show the percentage of attacks that succeed based on different numbers of features required to perform your attack. And what we find is that, for example, you can evade, or 90% of attacks on LSTMs only require modifying one single feature in the process data, whereas you would only be able to have a success rate of 53% against Cypress with the same level of access. And looking across the x-axis for different levels of feature access, Cypress is more robust across all those cases. Okay, finishing and summarizing part 3, I talked about designing ICS-specific models. Commonly, prior work uses deep learning models, which are inefficient, difficult to explain, and easily evaded. Because of this, we designed Cypress, a model architecture that focuses only on learning ICS-relevant relationships. And we show that by using these sparse structured representations, Cypress is more efficient, interpretable, and robust. So zooming all the way back out, I just gave a very quick overview of my entire PhD thesis, covering 3 major works. I'll pause for questions quickly before kind of doing some final takeaways and finally talk about privacy, which you've all been waiting for. Okay.
Fantastic. Thank you.
No, it's not done. Sorry.
I have a question.
Sorry.
Yes.
No, yeah. I guess when it comes to the actual integration of how these systems are operated, because I'm not too well informed, but what would you say is the starting point when it comes to whether it's the operators, the vendors, I assume it's the vendors who sell these systems, and then it goes through the the background people, they integrate it, and then the maintenance of integration. What is the hardest part, you would say? Is it the maintenance of ensuring that the AI is consistently working, or?
Yeah, I think the easiest way to get adoption in these settings is to kind of match the vendor interactions that already exist. So first of all, there isn't going to be a one-size-fits-all given the variety there. But for these systems, for example, they're just buying all their equipment and software from some vendor, I think the reasonable thing to do there would be to have the vendor be the one really pushing on the detection agents, diagnosis, etc. They're probably the ones who, assuming this is tying to the privacy part I'm about to talk about, but some sort of, privacy preserving or sensible way to train these detection models across their clients, and actually deploy them into these shared ecosystems. So I think that's probably the easiest way. But exactly, some challenges there are concerns about privacy, concerns about safety. If you're one water treatment plant, do you want data from the water treatment plant down the street being potentially influencing your operations? I think there's a lot of open questions there.
And do you want foreign nations?
Oh yeah,
I mean, to be able to buy those models.
All this stuff has to be in-house as well, and yeah, exactly that as well. Okay, just quickly closing my talk. Let's just talk about kind of what next, what I kind of envision in this space. As mentioned before, I'm going to touch quickly on privacy, and I think sure, this isn't personal PII necessarily, but privacy definitely still matters in this domain for ICS security, and that's especially because attackers can still leverage insider knowledge. One example that I'll use to kind of illustrate this is actually an attack that happened in Australia in 2000 on a sewage system. So what happened here, it's called the Maroochy-Shire attack. What happened here was that there was a SCADA engineer who, was terminated, probably not on the best of conditions, and decided to take revenge on their former employer. What happened here was, even though they had no extra access to the system, they had such intimate knowledge of the system that they used to work with, that they were able to buy and design a system with off-the-shelf radio equipment, and they knew that this system that they were working with was actually able to receive radio commands. And even from behind a fence, so a public road, they were able to send these malicious commands, as mentioned before, to manipulate the SCADA system. And what happened as a result was that 265,000 gallons of sewage was released to local parks and rivers. Marine life died. All the bad things that would happen when a sewage system fails happened. And I think that's really a good illustrating use case for why privacy kind of matters in this case. Because here, keeping your operations and your data private kind of implies safety and security of your overall system. So I think you wanted to protect your devices and protocols and the information about them. And it's kind of shown by some of these evaluations in this work. Existing defenses kind of are made stronger when you have some secrecy. For example, if you were to leak information about your machine learning model, it's way easier to compromise it with that knowledge. But as suggested by the question just now, I think the need for privacy in this space is really at tension with existing vendor reliance today. Right now, a lot of vendors are really involved in these ecosystems where devices are shared. If you have a zero-day vulnerability in one Siemens controller, that is going to have a really wide impact. And there's just dependence on these external vendors, even for security and diagnosis tasks. So I think finding a way to operate correctly and share this information in a private and sensible way, safe way, would really help, especially because there's currently a big mistrust of technology from untrusted vendors. I think overall, privacy-preserving technologies and defenses can really help enable a more secure ICS ecosystem. And then finally, very last thing I'll say is that just my grander vision for kind of bridging this gap. I talked about various projects about investigating practice to inform ML and then designing ML to and evaluating them based off of what we've learned from practice. But I think there's opportunities to really upscale this a lot. And what I think we need to do is to actually build representations and simulations of our critical infrastructure that contain both configurable simulations of the physical processes, devices, and communication used. So for example, realistically simulating the physics of a small town, a medium town, a large town, and the different devices and networking protocols that might exist. And using these simulations to create data sets of actual diverse scenarios in a way that's also standardized. So, diverse training distributions, the power grid during winter or the power grid during summer, for example, and diverse attack behaviors across different types of sensors, actuators, and different goals and levels of access. And I think with this, strong standardized set of simulations and data sets, we can really then start to actually build machine learning models that are well equipped to handle this broad range of scenarios. My research really showed that you can't just focus on a couple case studies to design an effective model. You really need this broad range of attack behaviors and training scenarios. And furthermore, I think once this is really set up, there's an opportunity to leverage even more recent research. What I'd like to do is build standardized, realistic ICS environments to benchmark new machine learning models for systematic progress in AI-enabled ICS security. And what I think this also could enable, even a little bit further down the road, some autonomous interaction. There's some research right now that has shown that you can use agents to pen test, red team your systems, and I think that if you have this robust standardized environment, you can really get to that as well. That's actually the end now. Thank you very much for your attention.
243 slides.
Yeah, mostly transitions,
Pretty impressive. So I want to say that you did a very nice job at connecting these two, confidentiality and privacy. But in general, for the past few years, this seminar has been about more than just privacy.
Sure. Yeah.
We do a lot of responsible AI and AI governance, which is obviously closely related to privacy engineering. Your presentation clearly had a lot to do with responsible AI, looking at the human side of things, looking at explainability, potentially coordination among different actors, protection against attacks against the models. And so I think from that perspective, that was a great illustration of all the challenges that we are facing when it comes to deploying AI in practical environments. Really great presentation. Thank you very much.
Yeah, and I'm still happy to take questions.
Yeah, we have a few minutes left, so if you do have any questions, we have a little bit of
There was
time.
one question in the chat, and that question, let me see if I remember. It said, I wonder if redundant sensory systems are used in ICS systems in practice. It may be important for the case any sensor data is wrong, quote unquote, or maliciously altered by a malware. If so, does your system consider redundant systems?
Yes, so in these interviews, we actually did learn of built-in redundancies. So a common thing you could do is to read your sensor from 3 different connections and take the majority built there. Problem still, I would say, is it doesn't totally make you clear of, let's say, attacks, right? At some point, there's some single point where, let's say, there's a network that feeds into your controller, feeds into your user interface or your anomaly detection model, and that's another point where you can really have attacks cause harm, even though you have, let's say, correct readings at a lower level. I think the real challenge is that these systems are so distributed and use so many devices that it's really hard to find a single point where defense definitely makes sense.
On a related note, sorry, there was a question.
Yeah, it's right behind. So, yeah.
So you mentioned at the beginning that practitioners, most of them didn't know how this worked. That's why you guys reframed how you were approaching them. So how confident are you that, with what you're building or what the research you're doing, practitioners will actually start using ML to improve the critical infrastructure security?
Yeah, I mean, that is a huge question, a big question there. I would say that, maybe the systems today and the environment today isn't totally amenable to ML adoption, as outlined by all the different things I just said in this talk. But there's definitely still, let's say, that need and motivation. It's not, I didn't cover it much in this talk, but in general, these systems are kind of outdated. The humans that work with them are really overwhelmed. They could definitely use increases in efficiency to help them. sure, they don't really trust what's out there today, but there is like a breaking point, and it's happening sooner than later, I would say. So there's definitely like a need, I think, to kind of help with securing these systems.
A lot of industries are resistant to move out of legacy software. So is that also something that you're taking into account when you build your ML model?
Yeah. So yes, just to comment on that, yeah, definitely. So if you have like a water treatment system, you're not going to like shut it off overnight for updates. Like, that just can't happen. That being said, there are still like vendor supplied updates that happen. Like things can be updated at a much slower rate than IT systems. And that's why I kind of see vendor, like you already have these existing trusted relationships. And that's why I think vendors actually can be the right place to introduce AI into these environments.
Great. And I think with that, we're actually at time. So maybe we can give Clement a last round of applause.
Yeah, thank you.
Great presentation.
Thanks.